Figuring out what time it is on the Arduino is really easy, but there are some errors when you measure that time. And we've got some stuff buried in this Jupyter notebook about taking derivatives of noisy data. I'm just going to move down here to where it talks about how micros and millis aren't really accurate. Now the micros function returns an approximate value for the number of microseconds since restart, and the millis function, which should have parentheses on it, returns an approximate value for the number of milliseconds since the microcontroller was restarted. And they both return unsigned long integers, and that means that they have a limited resolution to whole number values of microseconds or milliseconds. But it's even a little more complicated than that. The micros function only ticks over to a new value every 64 clock cycles. So when the microcontroller is rolling along at 16 megahertz, so 16 million times a second, it counts up to 64 clock cycles, and then it increments the counter for microseconds. So the microseconds counter is always behind, and it's only changed every 4 microseconds. So as a result, if we wanted to know what the time was in micros returned by the micros function as a function of the actual time, we'd have to take the value that we've got and figure out how many 4 microsecond steps that had been since the reset time. Then we would take that number of steps, this is going to return a float value. If we use this floor function, that'll give us the largest integer less than or equal to that value. And that'll give us the time that micros would return in 4 microsecond steps. Divide it by 250,000, and that'll give us the time that micros would return expressed in terms of seconds. So that'll be a time that jumps at 4 microseconds per step. Now millis is even more complicated because every time micros ticks over, it'll also count something on the counter for whether or not a millisecond's gone by. And it's only going to tick over to a new millisecond every 256 microsecond ticks. So every 4 microseconds it ticks. 256 times 4 is 1,024 microseconds have to go by to get counted as a millisecond. That means that we're going to lose about 24 milliseconds per second, so that every 24th of a second we're going to have to catch up. And the code inside the Arduino looks after that. So this code here we can use for simulation to see what's likely to come out of that. And this will give us about the same kind of behavior as we actually get out of the real Arduino. So let's just have a look at it. This millis function is taking the time up until the last round 24th of a second. Then it's dividing that into even numbers of milliseconds, and then figuring out how much time has happened since then, but slowed down by this factor of 1,000 over 1024. Finally, it puts it in even milliseconds for that slowed down value, and then returns the combination of the two. So the details here allow us to make estimates of what the Arduino will think the time is when we know what the actual time is. And so here I'm going to take, I've already got a variable t called time called t. I'm going to figure out what does the value of t in milliseconds look like returned by the millis functions as a function of t. And likewise, what does the time in microseconds returned by the microseconds function look like as a function of t? And what I can do is I can see how much that differs from the actual time by taking the time minus the time returned by the micros function, or the time minus the time returned by the time minus the time returned by the millis function, or the time minus the time returned by the micros function. And the one for the micros function here, I've scaled it up just to make it visible. Scaled it up by 100 times. So let's see what happens here. I'll run this cell. That just generates or defines those functions. And then I'll run this cell. And sure enough, what do we see here? Well, the time in millis ranges from anywhere from right on time up to almost 2 milliseconds behind. And it varies depending on just when we're checking it. Likewise, the time in microseconds varies from about 0 microseconds behind up to almost 4 microseconds behind. And it also is variable with time and fairly noisy. We can see that this millis function is really structured. Every 24th of a second, it's changing. So as a result, we can expect our values to be incorrect if we're choosing a time base, particularly based on the millis function, by up to 2 milliseconds per time measurement. So we'd like to use the micros function because we know it's always going to be within 4 microseconds. And we'll look a little bit later on at this taking derivatives spreadsheet to see what effect this timing inaccuracy has on our overall calculation of some derivatives.